we'll make a start now then. So yeah, good morning everyone. This morning in the whole energy systems kind of seminar series, we're lucky to have Mark Barrett and Tiziano Gallo Cassarino from UCL. So the structure is going to be that Mark's going to present for about 15 minutes, and then Tiziano is going to present for about 15 minutes, and then we'll have questions after that to both of them. So I'm going to introduce Mark, and then Mark is going to introduce Tiziano during his talk. So Mark Barrett has a PhD in energy systems modeling and is professor of energy and environmental system modeling at UCL, which he joined in 2006. He has 45 years of experience of modeling energy and transport systems and atmospheric emissions, working as a civil servant, consultant, company director, and academic. Mark has worked as a consultant for the European Commission, the European Environment Agency, UK government, the Japan Clean Air Programme, local authorities, private companies, and consultancies. He has specialised in the modelling of options and policies for managing energy use, greenhouse gas, acid and air pollution emissions. These models have covered all major sectors of demand: buildings, industry, transport, road, rail, shipping, aviation, and supply, fossil, nuclear, renewables, and have been applied at all scales from city and national and international. His most recent research has focused on zero-emission energy system designs from city to national and international scales, with a focus on heat supply. So, Mark, if you're ready, please take it away.
Okay, well, I think I'll introduce Tiziano first, so that we have continuity in the presentation. Tiziano, we started working together about 5 years ago now, and previously he was working on really difficult things like bioinformatics and proteins and these kinds of things. And then he decided he wanted to do something to do with policy. So he came into the simple world of energy modeling, and he's the first person I've worked with who I've given up coding. So I've given it to him. And so we developed the ESTIMO model together, but the computing side of it and Python and so on is really Tiziano's main contribution, but also in developing the scenarios that we'll look at a bit later. Okay, so
while Mark's getting the slides up, I'll just say, if you've got any questions, please pop them in the chat and we can read them out at the end, or at the end of the presentation, you can use the raise hand feature in Zoom and ask a question that way. Either is fine. Okay,
so I'm going to say a little bit about the model and the application. When the zero emission target was set in 2019, we had to rejig really our model focus to come up with zero emission designs which used no fossil fuels and largely relied on variable renewables, which is quite a challenge as compared to using stored fuels like fossil fuels. So we embarked on a project not only to develop ESTIMO, but also to apply it to looking at heating options, which Tiziano will say more about later. Yeah, so we designed 9 systems with different options of heating and different capacities of different components. And as I'm sure you all know, the basic problem is we have variable renewables here, which will be the largest contribution of zero emission energy supply. And of course, solar and wind have no integral storage. So we have to, given the hourly variation in demands for energy driven by social activities and the weather, we need to come up with a system of storage and different components to reliably meet demands hourly. And the thing is that these energy systems apply at all scales, from the building or even the heat pump system through to city, through to national systems and international systems. And these different scales are important because there are options, for example, internationally, which will reduce costs at the local level. And so we looked at the main primary energy resources and the primary, the main vectors considered. And we tried to come up with designs which were partly informed by optimization, but quite a large extent by manual exploration of different designs. So given a set of energy services, how much can we change the service levels with efficiency like insulation? And how do we harness these primary sources utilizing different conversion devices like heat pumps or electrolyzers, coupled with storage of different kinds and interconnector capacities? So we focused on renewable solar and wind resources because these are indefinitely large and you can supply any really any amount of energy that the UK might require, and indeed Europe. Whereas biomass and hydro and geothermal are important, but they're very limited in the UK and generally actually, apart from say a country like Norway, a small country where it's nearly 100% hydroelectricity. We excluded new nuclear power beyond Hinkley for reasons of waste and cost and generic risk. So we've just assumed there'll be 3.2 gigawatts in our long scenarios. We've excluded fossil fuels completely because they produce greenhouse gas even if you have carbon sequestration, and that has to be balanced with negative emissions. And we've reserved biomass for aviation fueling as there's no kerosene substitute. The starting point with our modeling is always looking at energy service demands. And so we have detailed modeling of the different types of demand: lighting, cooking, water, space heating and cooling, and so forth, in the three stationary sectors: domestic, services and industry. And then in transport, we have road and rail and ship ammonia fueling. And these demands vary partly by socioeconomic activity patterns, which we have a lot of detail on, and also for heating and cooling and lighting by meteorology. And heating and cooling, by the way, it's not just buildings, but vehicles, also electric vehicles, which are just buildings on wheels, basically. And then we have a national level modeling where we have the demands again here in the four sectors. And over here, we have our primary sources, which will be renewables here, renewable electricity here, biomass coming in here. Then we have gas, solid and liquid, fossil fuels, but we don't use those, and then some nuclear in here. And also, of course, we have trading across the national border with other regions of Europe. And in the middle here, we have the intermediate transmission and conversion and storage system. So for example, electricity comes in here, some might be stored, some might go to heat pumps to produce heat, which goes into the district heating system here. And the district heating system will have storage there in the district heating and can use multiple heat sources, CHP and boilers and geothermal. Then we might use electricity to make hydrogen with electrolysis and use that with the Harbour process to make ammonia for fueling ships. We haven't really done aviation fueling yet, it's more complicated. And then of course the electricity can be directly used in electric vehicles and heat pumps and so on and so forth. Now, what we discovered early on is that if you have international trading over interconnectors, then this reduces your storage need to absorb variable renewables by the order of about 30%. So we did an analysis early on looking at the whole of Europe and the electricity demands and the renewable generation to see the impact of storage of assuming the regions of Europe were not connected and then assuming that they had enough interconnection to absorb any local surplus or deficit. And so we run this national model here. We run 5 of those national models concurrently at the same time for 4 regions of Europe and Britain. So we're running 4 national models and then looking at the trade between them. And obviously the wider your geographical spread, the more that demands are evened out, partly because of meteorology and partly because of the clock times, of course, are different as you go east-west, and also because the renewables are averaged out. So at one point you might be exporting from Britain to, let's say, Eastern Europe. Another time you might be importing into Western Europe from Northern Europe. And perhaps one of the most difficult parts of this was the algorithm to control these flows of energy, both within the countries and between countries, between their stores, the stores of energy. So we developed this global optimum dispatch algorithm, GOD for short, which controls the whole system internationally and nationally. And it's an algorithm, but it could be a proof of concept for a dynamic energy market, which is one of the complex things we need to look at. And the basic algorithm has 3 phases. Phase A, you try and meet your demands locally using your current renewables. And if you don't have enough, if you have too much, you have a surplus, you try and store it locally. If you have a deficit, you try to meet the demands from storage. And that leaves with each node with demands all met or a surplus or a deficit. The second phase is to trade surpluses and deficits between the countries or the regions, again using surplus uncontrollable renewables and trading to and from storage, obviously within the transmission capacities. And then the last phase is, if you still have remaining demand at a node, then you use your local storage, for example, running district heating CHP using electrofuels or biofuels or natural gas. And then the final option is, if all that fails, is we assume that you provide dispatchable electricity using dispatchable natural gas stations. But the systems we've designed and we've tested over 35 years of meteorology data, we do not use the option of natural gas or any fossil fuel at all. So it's a completely renewable and slightly nuclear system. We've collated 35 years of mirror data, temperature, wind, and solar. And the temperature and solar data are weighted by population distributions for each country. And we use that temperature data to drive heating and cooling demand and solar. And we use the solar for driving PV modeling. We assume that's near to population. And the wind speeds at wind farm locations for generation modeling there. We had a bit of a look at the climate projection because, as Tiziano will show you, we investigated the implications of increased temperatures because of global warming and the effect on heating and cooling. And one of the critical things is the demand modeling side is the effect it has on variation. So we see an example here of heating and the demands for ammonia and so on. And you can see the typical diurnal pattern plus weather variation. And here we see the electric vehicles, that their demands also change substantially with meteorology. And as you've seen, here's an example of primary energy there, but you'll have seen all that. An example from the mirror data used to drive generation calculation. And then finally, heat demand. We looked at heat demand as important because about half of UK CO2 emissions are from heating. And this fraction is increasing. As the electricity decarbonizes, you're left increasingly with natural gas, which obviously has CO2 and methane emissions. So about half of CO2 or greenhouse gases is from gas heating. And so we looked at future heat demand. We assumed conventional heating systems, but one of the things that should be looked at is personal comfort services, with rather than heating or cooling the building, you heat or cool the furniture that you sit on. So I'll stop there and hand over to Tiziano.
Thank you, Mark. So I can share my screen.
I've got to stop the share somehow.
Otherwise, Mark, if you prefer, we can use yours. That's fine.
No. I think not quite sure how to
Right. Mark, I've stopped your screen sharing.
All right, thank you.
Stepped in. Tiziano, are you able to share, or do I need to make you a co-host? Let's check whether you are already or not. Yes. No, you're not. Hang on. So.
Thank you. Yeah, as Mark said, we're looking at the heating demand in shares, and we were in the credits. We were looking how we can investigate different heating system and their impacts on the weather system. And so we thought we could look at three main technologies. One is heat pumps on consumer premises, and then hydrogen boiler using green or electrolytic hydrogen. And the third would be district heating, which is basically a different way of distributing heat, because then you need like heat pumps or CHP or other boilers to provide heat. And so we focused on these three technologies, and we created 9 zero emission designs of the whole UK system. And we had three core scenarios where the majority of the heat was met by either district heating or heat pumps or hydrogen boilers. And so at 70% of the heat share, and the rest by consumer heat pumps or district heating. And then we also created 6 designs where we use the district heating heat share, just a reference, and then we change all other parameters like building insulation, generation capacities, and also interconnectors, as well as building insulation. And also we look at a couple of scenarios with different increased temperature due to climate change. And so each of these scenarios have different capacity for storage, interconnectors, renewables. And so we manually build and refine these scenarios in order to create systems that have zero emissions. And for example, the first 3 scenarios you see with the blue shade have different storage sizes. For example, for hydrogen boilers, we have around 50 terawatt-hours of hydrogen storage, while for district heating, we have like around 40 terawatt-hours of storage, plus some storage grid, which is common on all the scenarios. And also the capacity for PV, wind onshore, offshore, are slightly different to compensate for the different electricity and heating requirements. And for example, in scenarios where we increase generation, we kept the same other variables. And for example, we increased wind offshore in one case, or we increased PV capacity. And in other scenarios, we increase wind capacity, so more than doubling that. And also we look at different insulations level and changing the insulation parameters by plus minus 5%. So changing the temperature, the average temperature across the year, means that also the heat and cooling demand change. And so in the core scenarios, the total heat demand is around 460 terawatt-hours, and this falls to around 400 and 300.5, and when we increase the temperature in climate change scenarios by +2 and 4 degrees. And what changes in particular for the sensitivity of it and cooling? And so when we look at the building insulation and climate change, for example, with climate change, we saw that the heat demand sensitivity decreases by around 30 terawatt-hours each centigrade, while cool electricity demand for cooling increased more or less by the same amount. And we also see a slight decrease for electricity demand in road transport, basically. In the other couple of scenarios where we changed the building insulation level, we saw that a change in heat demand, so a decrease in heat demand by 3 terawatt-hours for each fraction of heat loss, and instead cooling, we saw a change of half terawatt-hour. And so this change in the weather are really important to design future systems because then the requirements will change. And we can see a bit better here on the right chart. The first top two bars shows the climate change scenarios, and we saw basically the blue line is the space heating, and the orange is the air conditioning. And basically, what happens is that the demand moves. The energy demand moves from winter for heating to summer for cooling, basically, because the total amount is almost the same. And one advantage I want to mention now is that through some technologies like heat pumps or district heating, the advantage is that they are more resilient against the weather and climate change because they can cool as well, so they provide more resilience. So moving to electricity demand, across the three core scenarios, so district heating pumps and hydrogen, the main difference is that due to the reduced efficient electrolyzers, then hydrogen boilers design require much more electricity. So 4 times more than the other core scenarios. And this is because of all the supply chain is a bit less efficient when we look at the green hydrogen. We look at the consumption of electricity, we look at not just the consumer, but also the intermediate system, so electrolysis and also the pumping district heating system, and losses in stores and transmissions. And just a side note, the electricity transport in all the scenarios is about 25% of total consumption, so it's not trivial. And basically what happens is that on the table you can see the electrolyzer needs around 5 terawatt-hours of electricity demand on an average year, which basically almost doubled. 70% is the increase in the total electricity demand. This also means that the hydrogen scenarios a lot of heat share from gas boilers need a lot of primary supply capacity and other production, and that translates to 80% more capacity compared to district heating pumps scenarios. And one thing we notice across all the scenarios is that since we need anyway a quite high capacity from renewables, then across the year the spillage is between 40 to 50%. We could decrease the spillage, but then we will need to increase storage capacity or the interconnectors to balance the reduced generation capacity. Or we need an auxiliary component that we run on other synthetic fuels. But again, there will be need to produce electricity anyway. And another side note is that since we need this high capacity for electricity production, then the UK is able to export electricity to Europe. Here we wanted to show what happens across the simulation we performed with ESTIMO. So before I was talking about the annual data, and now we can see what happens at the hourly resolution. So we run, this example shows simulations, some 3 simulations where we run 3 years of continuous weather data, and we watch what happens in the system. Basically, these are hourly flows for the storage and for the storage level and also demand. And for example, the top one is the heat demand provided by district heating using heat pumps, the blue lines, then some from storage, the orange, then there are some spotting there with CHP when ammonia is used. And then the pink line is the heat storage level. So across these 3 years, basically the storage has a seasonal pattern. So in winter we use more storage than in summer, where the storage get charged basically. But we saw that across these 3 years there are different periods where there's a heavy storage, heavy use of storage. And in particular, 2010 was let's say a bad year because there was low wind and low temperatures. And so we, at the beginning of 2010, there is a quite significant use of storage. So we use around half the storage in a couple of days. But then at the end of 2010, beginning of 2011, because of the very low winds, then basically the system has to use whole capacity of the storage, and so the pink line you saw there just drop almost to 0 for a period of 3 or 4 days in total. And then there are other periods when we need storage as well. And so the weather patterns are really important to design the size of, and all the requirements for the system if we want a resilient system that doesn't with a 0 emissions. And the other 2 plots are the same period, but so the first was on district heating, and the second is the hydrogen boiler scenarios, and the third is the heat pump scenarios. And so the patterns are always the same because of the weather, and also the use of storage is very similar because that depends on the weather condition and demand. And so independently of the system we want to use the energy vector, then we need to address the storage capacity and find the balance between supply and storage in any kind of scenarios. Just one note for the on the last plot for the heat pump scenarios, the grid, the electricity stored is also used for electricity demand. So the use of the storage is slightly different, so it's used a bit more than the other 2. Because we have a power, so the grid storage can provide also can help also to meet heat demand to give electricity to heat pumps out in district heating, for example. But we didn't implement the vice versa, so we don't use heat to produce electricity. But we use hydrogen and CHP plants in district heating. So going forward, since I talked about storage, basically what happens is that increasing storage can allow to decrease renewable capacities or interconnectors and vice versa. And so we need to take into account the whole system to really design resilient energy system. So for example, in the case of hydrogen, total storage is much higher because the system is a bit less efficient, and so we need more backup, let's say, solution, and increase, for example, the scenarios where there is a higher generation that comes from a higher, let's say, supply that comes from either renewables or from more interconnectors needs less storage because there's more basically there's more capacity available, and therefore less storage is less used, even in periods where the weather is when there is low winds, for example, and low temperatures. So now we will look a bit about the cost. We calculated for those scenarios, and we look at the capital cost, which are unitized using technology, unit cost, and lifetime, and we assume a 5% interest rate across the years. And since the core scenario, so hydrogen is taking in boilers, and in a certain amount of capacities for the renewables and storage, means that they have different values for these parameters, means they have different costs. And the hydrogen system, the hydrogen boiler system, needs more renewables capacity, and therefore has a higher capex, unlimited capex. You can see on the top right chart, and also the operational maintenance costs are slightly higher, with on average around 35% of the total cost. But so again, the hydrogen scenario is a bit more expensive than the other two core scenarios, district heating heat pumps. And this is also translates to the electricity cost for an average consumer, so the pence per kilowatt hours, which are slightly higher in the hydrogen boiler scenario. And so given that the other costs are roughly the same, so for the networks, even though for heat pumps hydrogen, these are a bit higher, the total cost for the hydrogen system are a bit higher, and these are followed by the system with heat pumps, because the as we see here, the cost for the consumers a bit higher, because they have to buy all the heat pumps for their premises. So if we accumulate the cost through all the components, consumer heat pumps have higher capital cost for consumer than hydrogen boiler or district heating connection. But then there are other costs upstream of the consumer, and the main difference occurs because the greater consumption of the hydrogen system, and therefore also the cost of the supply are higher. Looking at the both at cost and emissions, we can compare system using renewables and system using natural gas. So with the renewables, we have zero emissions, and there will be the three core scenarios: district heating, heat pumps, hydrogen boilers. And the system, as we saw, the system using hydrogen boilers is more expensive than the other two. Then looking at the system using natural gas, with zero net emissions, we can look at boilers, then blue hydrogen, and also CHP, and in district heating system. These costs basically are quite uncertain, particularly because of the future gas prices, and the technologies to reduce emissions, so data capture, CCS, for example. And so, but we can see from the chart that these costs are generally lower than a system using treated hydrogen, but they are higher than the solutions that uses the system that use heat pumps and district heating through again large heat pumps. And so the question here is really what technology we would like to use in the next decade, not just from the emission point of view, but also about the cost. So just a couple of things about the security of supply and regarding the system we simulated and the resilience. So basically we look at hourly simulation of system across multiple years. An example, I show 3 years, but we also run simulation across 35 years of historical weather, where we build system that don't use biomass or fossil fuels, and these are resilient against climate change because of reversible heat pumps that can provide heat and cool. We didn't check of electricity failure because periods with low wind would incur a much lower production of electricity compared to some technical fault in the system or an attack, because the generation is distributed on a large geographical area, and also in case of district heating, for example, or consumer pumps boiler, all the systems are distributed. The unit capacity we used in the scenarios was around 5%, so it was very small. And then we could argue that we can have other measures as a backstop capacity or to reduce the risk of low supply, using, for example, some gas turbine like 100 gigawatt. And they would add around 4% of total system capital cost and 2% to the annual system. But in that case, we will need natural gas storage, for example, to retain properly existing storage. So in summary, through this project, we look at different zero-emission systems that we designed to have commercial available existing technologies, except for hydrogen boilers, in some part heat networks, and they have no emissions because they don't use fossil fuels, and we exclude biomass because it's quite tricky to calculate emission from there. And also we look at a very long period of time to see whether this system could cope with different weather conditions. And we saw that these three technologies, the green hydrogen boilers, would be the most expensive because they require much more primary capacity from renewables. And what we can see is that all these systems will require major changes either on the consumer premises or on the whole system along the supply chain. Since we manually designed this system, these are not the global optimum, but still we managed to minimize all the components of the system to create a system with zero emissions. And the next step we are considering is to include the production of aviation fuels and look at the negative emission technologies like direct air captures, and increase the detail of the modeling on insulation and, for example, on efficiency, and look at more in detail about industrial application for hydrogen, like for iron and steel, and incorporate district heating into this, district cooling to integrate district heating into this system to see the advantage of these solutions, and perhaps looking also a bit more about the passive measures to decrease demand, like fabric or other batteries at the consumer premises. And of course, then the question is to understand whether modeling a system with a wider geographical scope, so connecting Europe to Africa or Asia, would decrease the requirements for the European system, and also see how we could optimize the system automatically to find other least cost or least emission systems. And I guess that's it. If you please feel free to ask us any questions. Thanks.